Okay, so I didn't get to talk about random Fourier features in the previous video, so I want to do that now. And the first thing I want to do is to connect Fourier transform to positive definite functions in the sense of what I had last time. I'll remind you of what I mean by that. So in general, let's say big K takes Rn times Rn. So X is just Rn here, and let's say C. In practice, again, it's real, the real. So K is positive definite if for any natural number n, any alpha in Cn, and any x in uh, uh, x1 through x big N. Um, each one of these in Rn. We have the following inner product. K alpha alpha on Cn. Yeah, this is bigger or equal to 0. Now remember what this is. This is simply K evaluated xi and xj. So it's an n by n matrix acting on alpha, the inner product of alpha. Okay. So how does this connect to the Fourier transform? So let's say we have script K is L1. Let's say it's continuous. And let's say its Fourier transform is also in L1. So in particular, I can use Fourier inversion. Then the claim is as follows, and I'll only prove the easy part of this. So this kernel here is positive definite on Rn. If and only if the Fourier transform bigger or equal to 0, almost in. Right? So yeah, I'll only prove the easy half. So this is what I need to prove. So let's form this matrix here. Right? So I'll just write out this inner product. And it's really just easy consequence of Fourier inversion. Right? So in particular, assuming this is true, I'm going to prove that K is positive definite. And that's almost all we need for K to be the kernel of a reproducing kernel Hilbert space. So I can use K for regression purposes. I also need the symmetric property. We'll assume that in a second. But for this fact, we don't need the symmetric property at all. Right, so K of xi xj is going to be script K xi minus xj. And so this is going to be Fourier inversion. So just write this out as an integral. So it's e 2 pi I xi minus xj inner product omega. Right. Yeah, let's compute this. I might be able to see where this is going. So this is just the sum n k xi minus xj alpha I alpha j conjugate. So I'm just going to plug this. Sorry, I got a w the omega. Just plug this into here. That's all I'm going to do. So this is going to be equal to. I'm going to take it the sum inside the integral with finite sum, and I can do that. So it's alpha I alpha bar E. And what I'm going to do is break this up into e to 2 pi I xi dot omega, the obvious thing here. Dot here, omega. As always, my omegas are basically w's. And because it's minus the complex conjugate, 2 pi I j does that. Right. Yeah, so just plop this in. 2 pi, we're almost done. We have Fourier transform here. Okay, but what is this really equal to? Think about it. That I equals 1 to n alpha I e to the 2 pi I x I omega. Then same thing, different letters, but it's really the same thing. J equals 1 to n alpha j. Careful space here. This complex conjugate times a Fourier transform, but these are the same thing, right? So finally, this is going to be following. It's the same thing times itself, complex conjugate. So it's just modulus squared. In some sense, I don't care what this is. It is non-negative. That's what matters. My assumption is that this is non-negative almost everywhere. So this is non-negative. Always this is non-negative. This is non-negative almost everywhere. So I don't care what alpha is. I don't care what the xi and the xj's are. I don't care what big N is. This inner product is always bigger or equal to. And that ends the easy. So much more generally, and you can state this even for much more general Fourier transforms, is the following. Yeah, so if script k right. Right. So if this here continuous on n, then k of x, y equals, I need to assume it's also L1. So I don't need to know that the Fourier transform is L1 or is bigger or equal to 0 almost everywhere. This is positive definite in the sense it's talked about. I talked about in the previous video. So this is true if and only if there exists a measure mu, positive measure mu, where script k is given by basically it's a Fourier transform. This is basically a probability measure. It's just that the measure of all of Rn need not necessarily be 1. It could be something, it's not negative, but it's something other than, it's not going to be infinity. Right. So, right. So it's basically Fourier. It's some sort of Fourier. So prototypical example here. So particular when mu is just the Fourier transform dw and script k and Fourier transform in L1, or we're assuming the Fourier transform script k is in L1. That's just Fourier image. So one direction of this follows exactly what we just did here. The easy part. If k is given by this, then the script k is given by this, then this k here is positive definite, the exact same proof that we just did. So yeah, some examples here. Typical example is a Gaussian. And even though the Haley-Wiener space kernel doesn't exactly fit what I wrote down, still the consequence is true. Let's say k of x is just this Gaussian. Let's say lambda is a positive constant. Take the norm of x squared. So the Fourier transform is positive everywhere. So this is a kernel. Take this as positive definite. Certainly this is symmetric. Um, it's, I think I have my constants right. Whatever. That's fine. It should be omega. Right. Yeah, so this is certainly bigger or equal to 0 almost everywhere. So this is a right, and we know I mentioned in the last video that this here, I think I use gamma, whatever, I'll use lambda gamma. Well, I mentioned that this defines a reproducing kernel. This is the reproducing kernel of a reproducing kernel Hilbert space, and in particular, from what we just proved, this is positive definite. This is certainly symmetric. K of xy is k of yx. Good. Another example, again, doesn't quite fit the assumptions we need, but the consequence is still true. So remember, if we have write this. Let me do this. Let's say rho of omega is going to be this characteristic function here. Right. So we computed the Fourier transform. Or let's compute the inverse. Yeah, that's right. We've computed the Fourier transform before. I guess I'll do x here. Goes to pi the omega over pi omega. And so the inverse Fourier transform is just the same thing as Fourier transform plug in minus x. So this is just sine. Well, clearly, plug in minus x. This is even. Okay, so let's say this is let's say script k is exactly this. Then the Fourier transform, just doing Fourier inversion is going to be at least almost everywhere this here. By Fourier inversion, at least almost everywhere. And it's the same conclusion. If k of x y is script k of x minus y, then that is the that's positive. Yeah, so I'm saying here, and here obviously x is in the real line, not Rn. Right, so the conclusion, this Cayley-Wiener kernel is positive. Okay, so something to note, then we'll get straight into random Fourier features. The point of what this is. If I assume this to be true, and I assume the Fourier transform is positive almost everywhere, then this naturally gives the Fourier transform is a probability distribution function, because it's used Fourier inversion. This is going to be n. So it'd be like really, it'd be like e to the 2 pi I 0 not omega, and that's of course 1. I'm plugging in 0, so it's silly to even write this. Right. So if this is non-negative, if this here is non-negative almost everywhere, the integral is 1. That implies this is a probability distribution. Okay. Right. And in particular, um, if you assume this is 1, then there exists a probability measure where this is true. Right. I mean, this has to be true. It's going to plug in 0. You would just get 1 is k of 0 is mu, the measure of r. It would have to be. So if we make this assumption here, or really just you take any k and just divide by k of 0 as long as it's not 0, then this mu has to be given by probability. Okay, so yeah. Right. So let's say, yeah, we're given so let's say much more generally, let's say we are given or let's maybe not so. Let's say we're concretely given we're concretely in this situation here. We can work with this more general probability measure mu, that's fine. But let's just say more concretely we're in this situation. Okay, then kind of doing what we've done before. And I can write this in the following way. So, right. So I'm kind of skipping steps here because I've done this before. This is going to be 2 pi I x omega e to the minus 2 pi I y dot omega. Fourier transform omega. Okay. Again, if you want to just write mu of w or d mu of w, that's fine. Being more general, but so maybe yeah, I guess I'll so in practice we're assuming k is real. So let's assume this is real. So this is going to be equal to the real part, which you can always bring in an integral. So the same thing. Right, it's a, so, the real part of I x dot omega minus 2 pi I y dot omega. Okay. So at this point, I'm going to make the following claim. This is actually remarkably easy. I claim I can write k in this way: 0 to pi n. So I'll write down what these are in a second. So this here is going to be square root of 2 cosine 2 pi omega x plus omega. So it's a little annoying in the original Fourier random Fourier features paper. They kind of say, let's pick be uniformly distributed and plug it in here. They're really just saying just take w prime and integrate it from 0 to pi. So this is just in the regular calculus sense. Right. So the proof is very easy. So the real part of this here, e to the 2 pi x omega e to the minus 2 pi y omega is going to be cosine, cosine, sine, sine. It's just check that super easily. So this is really more pain to write than actually anything. Try to write this very quickly. So what I'm going to do is I'm basically going to do the cosine some sum of angles formula with the product. Sine 2 pi x omega this. So I'm multiplying these two. Um, right. So I want to integrate the real part. So this. Yeah. So I'm not going to write everything out. It's just a freaking pain. But it literally writing everything out would, and checking is literally calc. It's like a challenging calc. Not challenging. It's a messy calc 2 problem. It's not challenging at all. It's literally calc 2. Um, yeah. So you can check using calc 2 that 1 over 2 pi, 0 to 2 pi. Um, so basically multiply these together. Cosine plus, and you're going to use the cosine, again, cosine addition formula, identity rather. Whoops, whoops, I'm getting an X. Sorry about that. Yeah, it's going to be the exact same thing. You can check that this is going to be equal to, well, exactly what I had. Out real quick. Uh, Second. Yeah, that's going to be exactly what I had. Cosine 2 pi omega. If you have any doubts, I would definitely check it yourself. I mean, it's not that bad. It's just, I know this video is going to be long enough. And it's really mainly, I just have a really crappy pen, and just writing stuff out isn't take too much time with my crappy pen. It's really the main issue. But I assure you, it really is a calculus. It's just calculus, not even calculus, it's calculus. Yeah, use the cosine twice. You're going to use the cosine um, uh, sum identity, the trig identity twice, and then just multiply everything out, and that's easy, easy, easy integrals. Sine 2 pi y. Yeah, and the point is really just take this and insert it here. You can, if you want to do, you can switch integrals with the same thing as saying this here. Right, so this here, here, let me make sense out of this. So, right, what I just outlined, I outlined that this whole thing here is going to be equal to the real part of e 2 pi I x w e to the minus 2 pi I y w. Right, and so that's equal to k of xy. Plot, just take this, plug it in, integrate against the Fourier transform. Okay, so we're good. All right, so what's the point here? The point is as follows. Right, so we basically have a product probability measure. That's exactly what we have. So 1 over 2 pi times the characteristic function of 0 to 2 pi prime, a hat w. Um, This is a PDF on Rn times R times Rn. And really, so what is this really? This is maybe it shouldn't look weird at all. This is really k hat times, so x just means times. So it's k hat times uniform distribution on 0 to that's really what this probability is. All right. So we have this written. So the point here is we have so I'm actually going to go back and write it the way I had it before. It makes this a lot clearer. This really gets to the heart of the point. So 1 over 2 pi 0 to pi and uh, uh, forget which order I had it in. It doesn't matter, of course, what order here I have it in. It could be order doesn't matter. I guess the way I have it here, it's if I have it like that, it's Rn times R, whatever. Order doesn't. Okay. So whenever you have a PDF, so before I do anything, this is obviously then expectation. So this is right. This is an expectation. And it's an expectation with respect to this random variable here for fixed. And it's a random variable in omega, hair omega prime for x and y. So whenever you take an expectation, there's a lot of ways to approximate the expectation. Monte Carlo approximation is probably the simplest. All right, so I'm going to do Monte Carlo approximation with respect to this. Okay, so I already have this claim here, so I'm just going to do a lot of erasing so I don't have to rewrite stuff. Okay, so let me erase all this. Wait a second. Now, I want to be clear, this is not the most efficient and best way to approximate, but it is the simplest way to approximate. Uh, so yeah, so for W1, WD, being IIDs, distributed from k hat, probability distribution function, and W1 through WD prime being IIDs. Distributed from the uniform distribution on right here. I'm going to erase this. Right, so just replace the expectation with the sample average. That's an approximation. And it's a reasonable approximation. We have theory that says this is a reasonable approximation. That theory is going to be Hooftings inequality, which if you do data science, you'll see over and over and over. Yeah, so I'll write it like this. This equals this expectation and omega prime, where this is from this distribution omega, and omega prime is uniform. Z W prime x Z W prime y 1 over D L equals 1 to D. Really just multiply. I guess I erased what this is, but remember this is just square root of 2 cosine 2 pi x W plus W. So yeah, you multiply square root of 2 together, you get 2. So concretely, this is going to be, well, let's not even do concretely. Let's just write it like this. I, that's what we did, so WL. And Z, WL, L prime of 1. And we can write this as a, yeah, I can write this as a inner product. And we're getting to the point here in a moment. Takes a bit of time to get to the point. As we'll see, the magic is with K in kernel ridge regression. If you have big N data points, you have to invert the big N by N, big N matrix. On the other hand, if you use this approximation, you can get away with inverting a D by D matrix, which is pretty remarkable. In practice, the number of Monte Carlo samples is much smaller than your number of data points. So yeah, I'll just state what Z, what the X is, Y is the same thing. Well, obviously you know what this is, and to be clear, this is on RD. Just writing this as a inner product, so it's just square root of 2 over D. My cosine, I can fit this 2 pi x dot W1, that's 1 prime. Did that square root of 2 over D, cosine 2 pi x 1, sorry, WD. That's right. And right. So to be clear here, the notation should be pretty clear. Yeah, so here, so I should have said this. This is just my vector of W's. And this is my vector of W. Okay, right. So yeah, if you've worked with kernel ridge regression with linear kernels, you probably can see the point now. That's essentially what we have here. We've converted K of XY into a linear kernel, just the inner product of these two vectors. But crucially on RD, so it's d-dimensional vectors. If you've never seen linear regression, multivariate linear regression, I'll tell you what the point is and why this is so remarkable. Right, so let's give this a name. Let's say it's K, for lack of a better call it K tilde. And yeah, thanks to Hoofding's inequality, we will get with high probability that K of XY is roughly this K tilde of X. I'll mention what Hoofding is. You don't have to know what that is. I'll mention it second. Right, so the point is as follows. This is approximately tilde of xi, xj. And what is this here? You can write this really as, we'll just write out the inner product. So when I write this L, I just mean the Lth component of my my Z here. So I'm just writing, yeah, it's just when I put L on top, it's just the Lth component. Fine. Yeah, so it's, yeah, like for example, this would be, notation's confusing. So this would be Z1, W1, W1 prime, Vex, and this would be ZD, WD, WD prime. Then these days I'll get something a lot better, something better. Right. Right. So just yeah, I guess it's silly to maybe let me this is kind of silly. This part here is a bit silly. So this yeah. So this really I'm just rewriting this. So this is just rewriting this. Z L prime J. If you think about it, this is going to be let's call this script Z transpose. Or this here IL uh, exactly what you would think it is. It's basically this IL. It's just this here. So now we're going to plug back into our original kernel ridge regression solution. And to the important sanity check, this is n times d, n by d matrix. So this is n by n. So we still have a big n by big n matrix. We haven't really done anything useful yet. We will see second. Um, so kernel ridge regression solution is y, let's say, is approximately j equals 1 to n alpha j k tilde of x j. Um, right. So let's just write out what this is. Right. So I'm going to first do, well, I guess I'll just do j equals 1 to n, l equals 1, d, alpha j, it's this z, um, l, l prime, x, and this is x, j. Uh, so what you could do is write this as, if you think about it. So what I'm going to do is first do the d summation. Um, sorry, first I'm going to do the, yeah. Right. So let me actually do that. Sorry. Okay, so yeah, so I want to write this as an inner product. Right. I remember concretely what this is. This is literally yeah, remember this is literally cosine 2 pi x omega plus omega prime. That's all this is. So let me get rid of a lot of this stuff here. I'm just going to remind you what this is because you get lost here quickly, I guess, otherwise. So remember, this is cosine 2 pi wx with w prime. Right, so exactly the same thing, but wl prime instead of w prime. Okay, but this here, black, you can write as j equals 1 to n. So this here, of course, this is matrix multiplication, right? I'm just writing it like this to make it seem like matrix multiplication. So this here, if you think about it, is nothing more then put it in here. Um, this here transpose yeah, L, J, alpha. J. Remember, if you transpose, you switch it. So really, the I is 1 through big N goes first. Transpose, it makes it go second. Okay, so right, you can write this as an inner product then. Right. This is going to be script Z. Um, okay. Yeah. So what's the point? The point here is we know what alpha is. Alpha, and I want to be clear. I'm taking yeah, I'm taking the alpha using my k tilde. So we know what alpha is. So it's well, it's the it's this one here, right? So it's this k tilde matrix that's given by phi. K tilde ij is this here. So this is going to be z transpose minus lambda the identity inverse and omega. Where the miracle occurs, and this is really a miracle, is from we have this here. This is what saves us. Yeah, you've seen things like this if you've ever taken a linear regression course. So I'm going to plug in for alpha right here. And I'll prove this miracle in a second. It's incredibly simple to prove. It gets a little tricky if you've never seen a trick. So lambda, I, and whoops, forgot the y. Sorry, got that. Should be y there. Remember, y is my output vector. So this is going to be, and I need to prove this. Save this. And make that bigger from the beginning. But anyway, so it's this matrix here. Transpose Z. But this is D by D. Again, this is absolutely miraculous. So I went from inverting an n by n matrix where n is the number of data points, you presumably have a crap ton of data, to inverting something d by d where d is the number of Monte Carlo approximations making. You can in practice set that to be much smaller than the number of data points. So this transpose sense. Okay, yeah. So I told you why this is so amazing. It's that when you compute this here, instead of having to compute an n by n inverse, where n is the number of data points, you can replace that with computing this d by d inverse, where d is presumably much smaller than it. Okay, so where does this miracle occur? And I'll end with Hooftings inequality. So in general, let's say A is X transpose X. So X is just some n by d matrix. I'm just replacing this Z with X. I don't feel like writing the omega prime, whatever. But in general, yeah, just take some n by d matrix. Doesn't matter what n is, doesn't matter what d is. So this whole thing is d by d, of course. let's say B is x transpose plus lambda I n times n. Right. All right, so what do I want? I want transpose. So here, right, so it's x transpose B inverse. That's what I have on the left-hand side. So this is going to be equal to A inverse x transpose x plus the identity times x transpose. If and only if, well, just do kind of something silly. Just multiply both sides by A on the left. Right. So this is silly, right? Again, this is what I need to prove here. Right. This is my X here. This Z matrix is X transpose. This is what I call B inverse. And then this is my A inverse. I think I might have that thing switched around. No, it's all right. So this really is very, very easy. Left-hand side is as follows. Just throw in A and leave B alone. So it's X transpose X. I don't feel like writing the identity, so I'll just write lambda. All right, so all you got to do is factor out an X transpose. I have one here, and I have here, so factor X transpose out. So it's going to be X transpose plus lambda B minus 1. But what is this? This is B. So I define as B. So yeah, if you distribute, this is trivial. I'm just factoring out the X transpose. Check yourself. Just distribute nothing. Right, so it's BB inverse. So it's this little trick to factor out the X transpose. And so we're done. Okay, last but not least, in what sense is this accurate? Now, I have an issue with this. I have a feeling the paradigm of who cares, it works applies here, but the pure math in me has a little bit of an issue with this. I don't really feel like this is practically justified via Hooftings inequality. I'll explain why in a second. I should consult some data scientists or maybe someone in the comments explain to me why maybe I'm wrong. But again, maybe it's just in practice it works, so who the hell cares? Respect that. Okay, so what's Hooftings inequality? What the hell does that have to do with doing? Let's say I have IIDs with mean mu and set SD to be the sample mean. So if you are familiar with Hooftings inequality, you should be able to see why this is pretty awesome. We're taking sample averages. We're approximating this expected value with sample averages with just the product of cosine. Actually, so this was square root of 2 cosine, I think. Yes, not the square root. Doesn't really matter much. And the point is, square root of 2 cosine, we'll take the product, that's between -2 and 2, no matter what omega prime we have. So this is perfect cannon fodder for Hooftings inequality, if you're familiar with it. If not, I'll tell you what the hell it is. So these are real valued. So if you can be a little more general, put a bound for each of the L, but here again we have multiplied together. We have 2 times the product of cosines. That's between -2 and 2. Um, so for any epsilon bigger than 0, we have probability that the sample mean or sample average rather, minus the mean is bigger. And epsilon is less than or equal to 2 times the exponential function minus 2 big D epsilon squared over B minus A. So what I'm going to do here real quick is the following. So I'm going to show, yeah, so what I'm going to do is get this inequality here. I actually get 8 here. I don't know how they get 4. I don't know if it's a typo or I'm just something wrong, but I got an 8. Who the hell cares 4 versus 8? But it is exponential decay. So I'm using a little bit different notation, slightly different notation. This is my k tilde of x. So they prove a global kind of estimate, and that's not particularly hard, but it would take a whole nother lecture to kind of talk about volume counts. And really, it's much more technical. But yeah, you can get like a much more global kind of estimate. But let's just at least see the pointwise estimate where it comes from, why it's almost immediate from who things. And I mean, there's really not much to do. And right, so let's say the L is exactly what this is. Yeah, product of these two, but with my sample averages plugged in, or with rather WL and WL prime plugged in. So multiply square root 2 by square root 2, it's 2. So this is going to be 2 times cosine 2 pi x L prime 2 pi y L prime. So this here is just right. It's just that my expectation. These WL and WL prime are picked as IIDs. Right. So y. So this is exactly my curve. This is precisely my curve. Point. While SD is going to be, well, we computed this before. I'll even write this out. So do that. Right, and this is exactly my approximate current. Yeah, this is right. I mean, this is just from our notation. It's exactly. Whoops, I think I got the one over. Also, I had the square root of 2 over d built in to get 2 over d. Right. So this is my my approximate term. All right, so the probability that this here for, and again, you can get a uniform bound, not that hard, but I just don't want to spend time doing it. So this really here, I'll keep doing that, so he's writing real line. This is tilde here. SD, again, we're assuming X and Y are fixed. So right, we're going to use Hooftings. Understand, obviously, that this is between -2 and 2 because cosine is between -1 and 1. 2 times cosine between. So this is going to be 2 minus 2, so you get 16. 4 squared, 2 would give you 8. So again, I don't know where they get the 4. I don't care. But so it's going to be minus 2d epsilon squared over 2 minus 2 squared. This is my B. This is my A. And this just gives you 8. So with high probability, if you pick D large enough, then yeah, you're going to have these kernels are roughly the same. So for a given tolerance epsilons, pick D. It doesn't have to be too low. At least this says that this guarantees at least somewhat that this is going to be a good approximation. This is K2. That doesn't necessarily tell you the solution is going to be a good solution to the original kernel ridge regression problem. I don't know if there's much theory out there for that. And another thing is, this is probability with respect to, this is the thing I don't like. It's with respect to this probability distribution function, k hat times uniform on 0 to pi. And that's not necessarily a physically relevant probability distribution function for real life, in the sense of, does that mean that there's a good chance, or there's a very small chance of this happening necessarily? This is just this artificial probability distribution function we needed to get this algorithm to work, this procedure to work. So that's the thing I don't like about this statement, but again, I think it boils down to this stuff works. It works well. So. And last but not least, the definitely active area of research is, in a lot of instances, why would you want to do necessarily the Monte Carlo approximation? In particular, if you have, like, let's say in particular, K, and I did this before, let's say K is sine 2 pi bx over pi x. And K hat is, well, just characteristic function of minus b. Well, sorry. So you would want just a, yeah. So you want this to have Fourier transform 1 at 0. So yeah. So you would want multiply by 2b, just modify this a bit, so that this is actually a probability distribution. So the point is to actually evaluate this integral. In this case, this would be just on real line. You're literally integrating cosine 2 pi x w plus w prime on a rectangle. It's literally a two-dimensional rectangle. So you can evaluate the double integral probably by Simpson's rule much faster than Monte Carlo. So the whole point is Monte Carlo is often not the best way to do this. And there's definitely, again, there's a lot of the active area of research on how to improve upon Monte Carlo. Another active area of research is you can try and pull this off somewhat whenever you have a kind of inversion formula that's given as an expectation. So familiar with like wavelets, short-time Fourier transform, Gabor transform. That is basically a wavelet transform. But you can try this. You're not going to exactly get this, but you can try to do something like this and just take a small Monte Carlo approximation. Someone actually a couple months ago did just this for wavelets. And I think they submitted it to a really nice conference journal. I'll put a link to the paper. It's kind of an obvious idea, but it kind of looks neat, and it looks like it's very quick and it improves things. This was submitted a couple months ago, actually. Yeah, definitely active area. All right, this was long, but this is in a lot of detail, nice and slow. So hopefully this helps. So I'll take care. Goodbye.